Wouldn't it be great if you could live forever? Living long enough to see humanity colonize a moon or a planet? Or eventually see floating cars? The achievements of humanity are undeniably amazing. With each passing generation, new discoveries and technologies help us understand the origins of life, enabling us to manipulate the surrounding world on an unprecedented scale. This curiosity and tenacity allows mankind to ask bold questions and find solutions using a combination of technology and science. One of these questions is arguably the most audacious of them all. Can we live forever? Irrefutably, our primary barrier is the process of aging. But what does it mean to age, and why does it happen? And apart from growing old, another barrier is disease. Well, what is disease, specifically cancer? Analyzing and understanding these complex questions will enable us to figure out how we might be able to use technology to bridge the gap. The human body is a complex machine comprised of a vast number of parts working as one to achieve a common goal: to provide a stable and sustainable vessel. Through the course of its life, the body could become vulnerable to disease, and as each vessel is different, the likelihood of heart disease or cancer depends on a number of variables ranging from external influences to genetic makeup. Contracting a disease has serious implications on a life. In 2014, approximately 14.5 million Americans were associated with cancer, with about 1.6 million more expected to be diagnosed in 2016. Incredibly fatal. Cancer is the uncontrolled growth of abnormal cells in a given area of the body. According to an American Cancer Society publication, from 1991 to 2012, the death rate dropped 23% because of reductions in smoking, as well as improvements in early detection and treatment. Notwithstanding the evident decline, researchers are still looking for ways to substantially reduce the death rate, if not to completely eradicate the threat of cancer. If the risk of disease can be eliminated, this could lead to a life uninhibited. However, like something built new, a human body begins fresh as a well-functioning vessel, eventually peaking at some point through the course of its life, followed by a steady decline and the inevitable demise, death. So, in short, all organisms have a biological clock, commonly referred to as age. Aging, or growing old, is the reactive process that the body goes through. Broadly speaking, an organism's body exhibits the health of its cells. Young and vibrant cells divide and replicate at an efficient and energetic rate with no error in the copying of genetic code. However, cells that are much older degrade and eventually copy DNA that no longer has expendable room for the duplication of chromosomes, thus leading to a lack of integrity in the overall function of the cell. This expendable room is known as telomeres, and it exists on the ends of each chromosome, preventing the skipping over of bits of chromosome after cell duplication. Or, simply put, telomeres prevent copy errors. When the telomeres have been exhausted, the cell will no longer divide, and when cells no longer duplicate, the body begins to wear down as there aren't as many cells to restore and rejuvenate the vast amount of functions. This cell duplication ceiling is referred to as the Hayflick limit, after Leonard Hayflick. Hayflick's research helped the medical community isolate the variables of aging, effectively confirming the astounding correlation between cell degradation and growing old. Beginning to understand why the body ages is a crucial step towards finding a way to either slow the process down or to completely stop it. Manipulating an organism's biological clock, let alone its cellular regenerative process, could prove unquestionably complicated. But perhaps, with the combination of innovative technology and science, humanity could find the path to immortality. So how do we start solving problems? Well, let's go back to cancer. There are several methodologies to treat cancer and tumors, the prevailing of which is to surgically remove the abnormal growth in tissue. However, the concern is more on the cellular level as opposed to the composition of formed tissue. Cue in mulitin, the toxin in bee venom. Experienced bee sting victims can attest to the pain felt by the sting of a bee. But in reality, it isn't the prick of the stinger that is painful, but more so the venom that is left behind. the agent is immediately killing cells in the surrounding area of the sting, hence the pain. The fact is that bee venom is an efficient killer of cancer cells, but unfortunately, it also does quite well killing healthy cells. There's also the problem of targeting a specific area as opposed to just flooding the body with melitin. If the specific doses of melitin could be carried directly to the targeted area, then researchers will have discovered an effective and efficient cancer treatment. Well, this is where technology steps in. More specifically, nanotechnology. The growing field of nanotechnology and the speed of its pragmatic approach and application have made this seemingly fictitious realm an eye-opening reality. Dr. Samuel Wickland, head of the Siteman Center of Cancer Nanotechnology Excellence at Washington University, and his team of researchers have designed a nanobot referred to as NanoBee. Aptly named, the little nanobee is comprised of different nanoparticles that hold the agent. Designed to safely flow through the bloodstream, the nanobees withhold release until it recognizes a particular chemical makeup of a cancer tumor cell that they have been programmed to seek. Once they find the target, they latch on like a bee and sting the cancerous cells, killing them. In preclinical stages, tests have been carried out displaying the effectiveness of the agent and the nanocarrier. This once seemingly insurmountable obstacle could be the mainstay of cancer treatment in the very near future. But if cell degradation and aging is essentially what leads to an inevitable morbid demise, then finding a way to slow or stop that process would be what ultimately yields immortality. The direct approach includes researching and discovering ways to alter the life cycle process of an organism's cells. This requires nanotechnology and the ability to build nanoscale bots that will carry out those specific missions. The technology needed to carry out such a task is at hand, as was displayed in 2014 by a group of chemists and engineers at Penn State University, as for the first time ever, nanomotors were controlled inside living cells. Tom Maluk, Evan Pugh Professor of Materials Chemistry and Physics at Penn State, stated that one dream application of ours is Fantastic Voyage-style medication, where nanomotors would cruise around inside the body, communicating with each other and performing various kinds of diagnoses and therapy. There are lots of application for controlling particles on this small scale, and understanding how it works is what's driving us. The ability to treat cells and provide long life would seem to have fewer barriers as humanity enhances its technological prowess. But instead of placing nanobots in our bloodstream to maintain, restore, and repair our cells, what if we simply replace the parts of our body that go bad? Organ transplants are already here and have been around helping those that are in dire need of a respective organ. With technology and innovation, humanity is on the cusp of artificial organs and engineered organ-level tissues. So instead of waiting until a moment that is forced upon an individual, researchers, using technology, are attempting to create a world wherein we simply replace parts that show signs of degradation. At the moment, technological advances in both material and design are allowing for failing heart organs to be replaced by artificial hearts. Currently, the device is used to help heart failure patients survive while on a long waiting list for heart transplants. But the expectation is that the mechanical heart will soon become the permanent solution. Without the worry of a readily available heart for transplant, even if the artificial heart isn't the permanent solution, what it could do is provide a reliable means to address the problem of transplant rejection. Patients who require organ transplant run the risk of rejection by the body, but if outfitted with a dependable mechanical heart, then perhaps the patient will live long enough for an identical heart, in the truest sense, to be grown and to be used as their personalized replacement. Otherwise known as organ-level tissue engineering, growing organs from engineered templates with the subsequent use of an individual's actual cells results in the personalized growth of an identical organ. The idea is intriguing for many as it would completely eliminate the risk of rejection by a person's body. Having grown the organ or tissue from the cells of the patient, it is indeed a body part that is completely identical to the one needing replacement. So, while we can't choose immortality today, technology provides the foundation whereon dreams could actually become reality. It's truly just a matter of time. Maybe one day we'll finally get to see floating cars.